Good afternoon, and thanks for joining me. It's good to see a few people here. You never know when you're the tail end Charlie whether I'm going to be here talking to myself at the end session, but it's good to see a few of you here to hear what we have to say. The great thing about my job as I travel the world, I'm based with Siemens PLM software division of Siemens. I'm based in California. I get a chance to travel the world and see our customers all over the world that are using our systems in manufacturing. From the biggest tool shops in China, like Foxconn, amazing, huge places. Just this morning, in fact, I was up in Derby at a well-known gas turbine maker, walking through their factory. They use our systems. And as I go around the world, I get a chance to see not only what are they doing in manufacturing using our software generally, particularly in my area. I have teams building machining software, CAM software, driving machine tools, driving robots and so on. I'm obviously interested in that. But I see what they're doing in 3D printing. And I was here a few months ago, just to start with a small story, I was here a few months ago in the UK, and I was with a company that makes very high performance race cars. I won't tell you who they are exactly, but you may be able to guess. And as usual, I get a tour around the plant. They use our systems for design, for analysis, for manufacture, of course, for the race cars. Very high productivity, high pressure environment. Speed is really important, throughput and so on. And we're walking around the plant and they say, come and look in here. This is our 3D printing room. So, oh, okay, this is interesting. Let's take a look at the 3D printing room. So we go in, and it's not too big a room. 1, 2, 3, 4, 5, 6 cabinet-style printers out there. Kind of dim lighting, not too much noise, maybe a hum of the air conditioning. Some of the machines are glowing, laser thing. It felt like a lab, Small components. I almost expected a guy to walk in with a white jacket and a clipboard to go and check the specimens out. And this is what I see very often when I see 3D printing around the world. In prototype shops in China, they use 3D printing, but it's in a small area. It's 3D printing for prototypes, low volume, they hand finish them. When I went back to this company again, the race car company, we came out of the lab, as I called it, the 3D printing room, and for them that was really high value. They're making small specialist components. They hadn't got time, nor they want to afford to make the tooling to make plastic parts. For race cars, it's a one-off, virtually. It's really high value proposition for them. But for me, it was like, doesn't seem like real manufacturing, not what I'm used to. We go down the corridor, we go into their main manufacturing facility, and then there's big machine tools. Overhead gantry cranes, things on the floor, they're machining forms as well for carbon fiber layup and so on. That's what I'm used to. But the 3D printing is not there. 3D printing's in the lab. And so it's interesting for me to take this subject as we as Siemens look at how we can help companies who are looking to push 3D printing, deposition systems out into the big full-size manufacturing part of their business. And that's really my subject, how we partner together with other people, other companies, to produce systems that really are industrialization of 3D printing. So three sub-topics for me are partnering, how we partner, how it's important for us to partner. We just don't have all the knowledge ourselves. We have to partner, and I'll speak more to that in the examples. I'll talk about multi-axis deposition. You won't see that here in the show, really. Multi-axis deposition as opposed to in-plane deposition like powder bed machines. Quite a different approach. I'll show you one example. I'll mention two examples, but I'll show you detail on one example here where we're partnering with Stratasys. And that example is the robotic 3D composite thermoplastic printing system. And then just to finish, a recap on the need to collaborate. So obviously most of this you understand, you're out there at the show, the obvious benefits of 3D printing, additive manufacturing, especially for low volume products or heavily customized products. This is where we know it works really well. High value due to complexity of materials, whether it's metal or thermoplastics, where strength to weight ratio is important. We see this with components that can be designed differently so they can be lighter but still have a great strength, of course. So these are all advantages of 3D printed components, especially if they're made of the right materials like composites, which are becoming more and more viable. But larger. So most of the parts you'll see printed here on those printers I talked about in the race car company, they're relatively small. And that's because most people are using fixed plane deposition systems or like powder bed systems, and there's a limit on the size of the cabinet, the size of the envelope. partly because of the amount of powder you need. It's heavy and it's expensive, right? So the parts tend to be limited in size and relatively small. That's what you'll see here. What I'm talking about today is completely different. We can produce huge parts, almost unlimited in size. And this is really one of the big value propositions for many companies where they look at parts that are therefore much bigger. And otherwise, for parts maybe that are otherwise available on very long lead times. So one of the examples I'll touch on, I won't go into too much detail, is a multi-axis deposition system using metal laser powder. And there we partner with a machine tool company because we modified a machine tool to do this. And one of the examples there we're working with is a company that makes rockets in the US on the West Coast. For them, the value proposition is enormous if they can print in metals like this, titanium coated with copper. Because the lead time on a casting, they use a casting otherwise, can be 18 months. It's casting in titanium, and then it's electroplated copper on top of that, which takes 3 months. It takes a very long time to produce the casting. And the real problem with that is not the delay, that's annoying, but the time taken between the date on which I freeze the design to when I've got the part. 18 months is too long. If I can print it in 2 months, on a metal deposition system, a multi-axis metal deposition system, then I get a huge value proposition for them. Some of the barriers to industrialization, repeatability and scalability, this applies to really across 3D printing. I need to be able to be sure, especially if I get into aerospace, of course, sure of the materials. How do I do that? How do I measure the process? If it's metal deposition, laser sintering, I can measure temperature, I measure the melt pool diameter. I can measure things that give me an indication of what the process is and how good the process is. But I need to add that kind of measurement. Thermology type equipment, for example, we need to do things that will give us the confidence, give our customers the confidence that the products they're going to be producing this way are going to be reliable to the right specification and so on. So this is a key area that people are working in a lot. A lot of it is material science, of course, but also a lot in process and how to measure the process such a way that I know if I measure this, then I'm going to get a good result in the material or the product. The materials themselves, composites, of course. I'll talk about composites more in the example today. Not just composites with short fiber, but longer fiber and even continuous fiber. And when you go to continuous fiber, then you open up a whole new ball game of strength to weight. I can really print in a multi-axis printing mechanism a continuous fiber composite product, then I open up a whole new world for us in terms of the kind of components I can produce. Scalability and flexibility, this is important. Again, if you take a laser, say a powder bed printer, it's this big, I can put one next to it, but I can't join the products together inside the printer. With the systems I'll show you today, they're very modular. We're using robots. We can add another robot or another robot. We can scale it and really make the system as big as we wish. So that's important when it comes to making this more industrialized. Automation is really important. Automation, we talk about that a lot in our systems, Industry 4.0. We want to automate the software, we want to automate the machinery, and so automation, or the ability to automate the process, again, is very much important for industrial companies, and something we do every day in our software for industrial manufacturing solutions. Higher order motion control. I'll be working in these examples in multi-axis deposition, so I need a 5, 6, 7, or 8 axis control system. I need to control the robot, I need to control the extruder, as well as maybe some kind of train system or tram system for the robot. And design for manufacture, design for additive manufacture and factory integration. So the way the CAD system works, it's important how we design the model, what CAD functions I have to do design, what analysis. Analysis is really important. We have a wide range of software in our systems for FEA, for finite element analysis, for heat. So heat dissipation, being able to predict shrinkage is a real critical, tricky factor in all these examples. Even with the thermoplastics, I have to be very much aware and ideally predict how the parts are going to shrink as I print them. If I let them cool too fast, when I come back again to print more material, they will have shrunk more than I expected. So having the analysis tool to predict how parts will shrink as I print them is really critical in all these systems. So if I'm going to be really practical with them, and as they get bigger. PLM, so PLM is an everyday term for us, product lifecycle management. As we industrialize our systems, companies have to fit them within their overall IT systems. They do that every day today with machine tools and so on, shop floor systems, presetters, shop floor software, design software, analysis software. It has to fit within an overall system where they manage the data, the revision of the data, the configuration of the data. They take that for granted and they expect it. So as we partner, one thing we can bring to the table is the ability to integrate applications that drive 3D printing into the equipment. That's the thing we do every day with our systems as Siemens. But it's an important part of the solution. It isn't just a standalone printer. It has to fit inside this infrastructure. So 2 examples, I'll talk to the one on the left very briefly, then in the time that's available, I'll talk to the one on the right. And which is the robotic composite thermoplastic example. The one on the left, we partnered with a machine tool company. Again, it's very, very important to partner here. If I'm doing traditional CAD, CAM, driving machine tool, I don't need to partner too much unless it's a very special machine, because the interfaces are very standard. I know how to drive a 5-axis machine tool. I don't need to partner with a company to work that out. My software and the teams that I have developing software can write software that would drive a 5-axis machine easily. But when it comes to this kind of equipment, it's so new, there's so many things we're both working out that we have to partner. They want to partner, we want to partner, because we want to get tied together to build a solution and develop it together. So in this case, we're partnering on the left-hand side there. It's laser metal sintering. It's multi-axis, which means the part is mounted on the base of a 5-axis machine tool, effectively, on a trundle, as they call it, with a rotating base. We build the part on that. We can rotate the parts, turn it over as we build. The laser deposition's on the top. And we can move this thing relative to the part in multi-axis. So we're depositing all the time out of plane. Quite different than the in-plane deposition systems or laser or powder bed systems you'll see on display here. So multi-axis, moving the part, depositing. We can deposit off angle, but all the time I'm computing the XYZ of the part and the XYJ of the direction of the tool, the printing, the laser relative to the part. Printing the metal is laser powder sintering. You can see a diagram of how that works. Laser down the middle, powder down the outside, and a jet of gas down the outside to control and keep the oxygen away. And we can deposit material. The distance between the end of the nozzle and the printing material, printed part, is about 1 millimeter, so it's quite close. So clearance is a real issue for us. But we can rotate that part and print on any angle. We can stop the part, and it's a machine tool. I pick up a machining tool, an end mill, and I can machine the part, finish it, finish the surface, and print again on the same part. So we call it hybrid, combination of printing and deposition on the same machine tool. On the right, the one I'll talk more about is the robotic composite thermoplastic. So again, our software from my team is driving the robot. It's driving the exact path of the robot as it handles the deposition head. This case is an extruder head there from Stratasys. And the components mounted on a separate device there, a positioner they call that can rotate and move and actually up to 8 axes. So partnering together, Stratasys brings the knowledge of the thermoplastic materials. We don't have that. They bring the information about the extruder, very, very fancy new extruder technology, multi-stage screw extruder that they use in this example here to deposit, to extrude and deposit the thermoplastics with embedded short length fiber. And then on our side, we bring the software, the NX software is the brand, where we create the tool paths to control the deposition paths, which are a very critical part. And then the motion controls from Siemens, from my colleagues in the motion control division. These are the Cinemeric branded controls to drive multi-axis equipment, the robot, the extruder, and the conveyor chassis on which the robot could run. So this is how we partner together. We couldn't do it ourselves, and we have to work together. So why multi-axis? So multi-axis deposition is compared to, say, a powder bed is 10 times faster, simply because of the motion. I don't have to go backwards and forwards across the whole bed. I haven't got to produce supports. There's no support structures because I'm not worried about whether the part's going to droop with gravity. I can just rotate the part and build upwards. So all the time I'm moving the part around and in multiple axes working upwards from the part. So in most cases I don't need support structures. Very rarely when I do, I can build support off the components and machine it away later. But typically I don't need support structures, so that's really a big advantage. The envelope can be massive. This robot can reach meters. If I put the robot on a rail, another axis, the robot can run the length of the room, no problem, and build on a very large bed. A wide range of materials, so that's got a thermoplastic extruder. I can put other metals on it. If I'm using a machine tool, I can use metal, as I've already described in multi-axis. These are both, the robot and the machine tool example are both good examples of multi-axis deposition. And we can use existing technologies like the robot. We can reuse a machine tool. What's happening now is people are experimenting with this. They're reusing equipment. So people are using machine tools and then sticking a laser on the side of the machining head. So they're kind of modifying equipment. People are using things like large-scale wood routers, taking the router head off and putting a deposition head for plastic on it. So we're seeing a lot of that at the moment. But what you're going to see over the next few years are people building purpose-built equipment, where the machines are like machine tools, but they're built to be deposition machines. So the markets for this is pretty traditional. For FBM, fixed deposition modeling. They're aerospace, automotive, aircraft interior structures. Composite tooling is a big industry here for potential industry too, for printed thermoplastic or composite components. Oil and gas, like wind turbines, for example, long blades, they're made of composites. They'd be ideal to print them today. Today it's laid up by hand or by layup machines, but we could print those. So a wide range of opportunities. Some indication of the market in aerospace, $13 billion composite component business here. A lot of it is we all know that composites are being used a lot more in aircraft. A lot of it is very time-consuming work, even hand layup in some cases to lay up the composite material. It's very tedious work. It's not that automated. So there's a big opportunity to go into this space if we can get long fiber deposition using robots, for example. Then we have a big opportunity here with this kind of equipment. Also, in the demonstrator, I'll show you the video in a moment. You'll see a video, two videos on the same screen in the next slide of the software on one side and then the machine running on the other side. 3 or 4 areas of different components in here. As far as the deposition head, you've got the screw, a deposition device, the extruder. You can see there in the top here, they've got a canister of powder, of actually pellets of thermoplastic with embedded short fiber. The pellets are actually made and designed for the right size and shape and composition by Stratasys. That set of equipment there on the top labeled the screw, that's Stratasys equipment there. You can see the liquefier, which is the other, goes down below it. These devices are all fitted together on the end of the robot. And then we have the air software, which is the software we use to do the basic CAD design of the components to be machined, but more importantly, the decomposition into the features we'll manufacture. So this is an important part. We have to look at the part we want to print in 3D in multi-axis and decompose it into the features. And then we use this information to determine the sequence, how we're going to rotate the part, which features we do first, which we do second, and how we move the part is important. So in NX, we look at the part, the model, we decompose it into features, we look at the build sequence we want to have. If we're going to do machining, we build that in two, if that's part of the process. And then we do the programming to take the part file as it is, the model, and work out the tool paths, as we call them. If it's machining, it would be tool path. In this case, it's deposition paths to deposit, to control how the extruder and the robot will move relative to the part. The bottom, that's a control system from Siemens, the Siemens 840D Cinemeric controller, a multi-axis control system used on many machine tools, used to control robots. In this case, it's being used to control the robot, the KUKA robot, and also to control the extruder. So it has a lot to do, and it's driven by output from our software, from the Siemens software. On the right-hand side, the components for robots is a KUKA robot, and the positioner, as it's called, on the right-hand side, they go together. You can see them in position in the bottom right in that work cell there, with all the equipment put together, ready to print. So in the next slide, you'll see on the left, there'll be 2 videos. Left-hand side is running in software. This is inside the Siemens software. You can see we're running a simulation there, being driven by the output code from the software, drives the simulation. You can see the part moving in multiple axes on the positioner, being rotated and moved, the robot moving to print. On the right-hand side, you'll see film in a moment of this running actually in production. So the advantage here is speed, say 10 times faster than a standard sort of powder bed type deposition system typically. Very flexible. We can print a range of parts on this, only limited by the size of the overall environment for the robot. There's no support structures, and we can get very good quality, surface quality out of this based on the material and the extruder technology. So here you can see the thing moving in multiple axes. We're actually extruding material as we go. Looking at the control system there. So this is a single robot. Now we could have a second robot, maybe doing another task, or if it's a very large part, we could have a second robot working on another part of the same structure. We could put the robot on a rail and move the robot along a rail so it's got an even longer reach. And that's all traditional standard software. We can do that today to drive the robot like that. We use those robots today to drive them for, say, polishing or deburring on metal parts for aerospace components. We do that today. So taking this robot and driving the extruder is just a different way of using the same technology. One difference is the paths. So the paths we've been using for many years to drive robots or drive machine tools, now we're using them in reverse. So instead of using them to subtract material, we're using the same kind of technology to define a path to add material. And it brings new challenges. So things like the bead width. Is it constant? Is it varying? What's the step over between different passes? And I have to consider things like the cooling rates. How soon do I come back and deposit material in the same position, for example? I have to worry about the angle. If I'm spraying metal with a metal laser powder system, what's the exact angle I can work to? How far can I go before I start getting overspray, for example? How about collisions? This is very, very confined space. I'm moving in multiple axes here, a lot of movement. I have to worry about collisions. So the software has to look at not just the product, and as we're removing material, I have to think about as I'm adding material, the part's getting bigger, am I going to know where that material is so I don't get a collision when I come back with the extruder or the powder deposition system. So we have to do a range of things differently, and we've been working now for 3 years on the metal deposition system, and about a year now with Stratasys on this thermoplastic deposition system. So this is a picture of the same, we had this machine running in the IMTS show in Chicago 2 weeks ago, and this is a picture of the same machine. What they did here to make it look prettier, they decided to hide the extruder head with all those pipes and tubes, so they actually printed before the show. The day before the show, they actually printed, well, it's Stratasys, so they would print it. They printed a cover to go over the extruder head. So you can see that black box with the blue light on the front. That's covering the extruder and system on the top there. Another example here showing photographs of some parts that have been printed during the show. So one of these parts there, like the parts with the ribs, that would take about 15 minutes to print. So it gives you some idea how fast that is. Really quite quick to print one of those components from scratch, including the inner cone and then the outer ribs on the outside of it. So use cases, I've talked about this a bit already. These are the sort of things we aspire to be able to print using this thermoplastic composite, especially as we develop the ability with Stratasys, as they develop the ability to print long fiber, continuous fiber. So not just extruding material in which short fibers are embedded, but to be able to run out continuous fiber. That opens up a whole new area of opportunity for us to be able to print aerospace components, obviously jigs and fixtures, automotive components, for example, where we can take advantage of the strength due to the directional positioning of the carbon fiber. So a range of opportunities here for the kind of products, large fixtures, for example, aircraft interiors, car components, and so on. Very large components compared to what you see typically coming off your traditional 3D printers. So some advantages, strength, especially if we get into directional composites. Think also if we're coming out of plane, we're not just working in a fixed plane. If I work in a fixed plane and I use composite material, I only get strength in one plane. Now because I'm working in multi-axis, I'm coming out of plane, I can lay down the composite in any dimension or angle I want to, and therefore achieve the strength of the composite material in the direction I want it. I'm not just restricted to laying out the fiber in a single plane. So there's a big difference. Speed, I talked about support elimination. I don't need to worry about building supports, which takes time. I don't need to worry about cutting the supports off afterwards, which is a problem. If I do traditional printing, you'll see some parts out here with all sorts of complicated supports on them where they've been printed in powder deposition systems. Flexibility, hybridization. What I mean by that is a combination of subtractive machining or measurement on the same system, so I can put the deposition head over one side, pick up a machine tool and machine the component, drill holes or slots in the metal, or polish the plastic, or finish the plastic, thermoplastic, or do measurement on it using probes or lasers or whatever. So I can have a hybrid solution on the same industrial environment without taking the part away and doing a different setup. And connectivity, I talked about this already. This is the connection to industry systems, whether it be ERP systems or PDM systems or CAD systems or MES systems or DNC systems. These are all systems that companies have and expect you to connect to when you put this kind of equipment in their factories. And just to talk about the workflow, it's an overall workflow going from product design through production planning, production engineering. This is what we used to, we do this all every day with our customers, and 3D printing, deposition systems have to fit within this overall similar workflow. Going from functional design, CAE, decomposition, I talked about that earlier, taking it apart and breaking it up in a semi-automatic fashion into the features that we're going to build, in what order the features are going to be built. That will tell me also the machining or build sequence, deposition strategy, how I'm going to, where I start, where I go next, how I rotate the parts to get into position, to build the sequence. Tool path generations, this is the generation of the paths to control in multi-axis code. And then simulation, so this is building a 3D model of the entire system. You saw that running on the left-hand side of the screen. Checking for collisions, anything else that could be wrong with the overall setup before I run it on the machine. That's machine tool simulation technology, and then post-processing, taking those instructions and then outputting them into the exact codes that the machine tool, or in this case the robot controller, will understand. Typically we call that G-code, and different variations of G-code to suit the machine, or in this case the KUKA robot. And then the actual control of the equipment itself out to the controller with those codes to drive the robot, to drive the rail, to drive the positioner, and to drive the extruder head, which can be varied in terms of deposition rate. All that has to be controlled and synchronized using the, in this case, the Siemens control system. In terms of the future, where we're going, so we're on the left at the moment. So what we showed at the show in Chicago was, we referred that to a demonstrator. It's not production ready yet, but the intent is to go into a production system where you have a robot running on a rail like this, printing things like thermoplastics or composite thermoplastics. Then going to larger machines like the gantry setup here. In this case, we've got a robot hanging on a gantry here. That's just a possibility. And then going to multiple robots, as I've talked about already, to really expand the envelope, have multi-function robots. Some robots could be doing other post-operations like polishing or drilling type operations on the parts. And then eventually to multiple systems, multiple gantries and so on, having very, very large components. Maybe you'd use those for turbine blades for wind turbines, for example. And then just to finish, for the need for collaboration. So we're looking at taking proven industrial strength equipment. I talked about machine tools. That's second nature for us to work with machine tools. Increasingly, those machine tools are going to be taken and built more specially for the purpose of deposition. Today, people are sort of taking machine tools and adding deposition heads onto them or lasers onto them. You're going to see a lot more examples of proven machine tool type machines of that sort of strength and weight, not like the sprinters of these out here, but machine tool type machines being designed and built for printing, deposition. New material technology, of course, we have to collaborate for this, as I said. Stratasys is an expert in terms of the materials and the deposition technology. We don't know that in our software division. Equipment like the extruders. So again, Stratasys developed the latest technology for the multi-stage screw extruder, which is really important. Gives us the ability to control the rate of extrusion, make the extrusion go faster or slower. That's really important. New and adapted software, so that's the industrial software from my team, software that's been used for many years to drive machine tools. Now we're using the same software or variations of it to drive deposition in multiple axes, the simulation, the post-processing, the connection to other shop floor equipment is all stuff that we're used to and have software to do. And then the integration with critical systems like MES, manufacturing execution systems, to monitor the process and other shop floor systems. So this is why we collaborate. and that's one of the overall themes of my presentation. In this case, the collaboration was mostly with Stratasys, also with KUKA, and with my colleagues on the control side of Siemens. So my name there, that's myself from Siemens, and also I've got one of my colleagues there from Stratasys, the Director of Advanced Manufacturing Technologies in the US, Clint Newell, who has been one of our team leads on the combined project here. So that's it from me. I hope you enjoyed this presentation on multi-axis deposition, and partnering for industrialization. Thank you.